Alright, we're going to continue with our discussion over quantum numbers. Here's kind of a little re-example of what we talked about at the end of the last video, where we have a principal quantum number of n equals 1. What are all of the possible other quantum number values? Okay, well, the next quantum number is the L number, and that one tells us what the orbitals are, and it's n minus 1. So if n is equal to 1, then we would say 1 minus 1, and that would give us 0 for our L value. Remember, I told you that the L values correspond to the orbitals and the letters of those orbitals, SP, S, P, D, F, which I told you previously, and that each of those letters corresponds to a number. So S corresponds to 0. I'll just quickly rewrite those back out. We had S, P, D, F, and so starting with 0, we work our way up the number scale there. So we've got S is the same thing as L equals 0, P is the same thing as L equals 1, D is the same thing as L equals 2, and F is the same thing as L equals 3. So here we have L equals 0, which is telling us that it's an s orbital. And since we're at the first quantum number, it's the 1s orbital. Okay, so then what can the values of m sub L be? Alright, to get that, it's going to be all whole numbers between negative L and positive L. Well, if L is equal to 0, then that would be negative 0 to positive 0, and since there's no such thing as negative 0, we just have 0. Okay, so the m sub L value, or the angular momentum quantum number, tells us what orientation the orbital is taking. Now, since the s orbital is a sphere, it really doesn't matter what orientation you look at a sphere at. It looks the same no matter how you rotate it. So there's only one way to look at that s orbital. Okay, and then we have the m sub s, or the spin number, and that tells you if the electron is spinning clockwise or if it's spinning counterclockwise. Okay, so I don't know, let's look at an example. Let's say we're talking about hydrogen. Okay, and we know that hydrogen's got one electron, and I want to describe that electron with the quantum numbers. Okay, hydrogen is in the first row of the periodic table, so that's going to give it an n, or principal quantum number, of 1. Okay, so then the L values. All of the possible L values are going to be n minus 1, so that would be 1 minus 1, which would be 0. So that's telling me that that electron is in an s orbital, so it's going to look like a sphere. Then we've got the m sub L values. That's going to be 0, because this is from negative L to positive L. And then we've got the spin. Now, since there's only one electron here, that means that we're going to have the plus 1/2 spin. It's going to be spinning clockwise. If there was another electron that partnered up with it, maybe from another hydrogen atom, then that one would have the minus 1/2 spin. Okay, so the address here, I suppose you could say, for this electron in a hydrogen atom would be 100 plus 1/2. Okay, what if we did helium? Okay, alright, well, helium is going to have 2 electrons, and I want to describe let's say I want to describe the second electron. Okay, helium's first electron is going to be just like hydrogen's only electron, but helium's second electron is going to be different. Alright, so let's go through that one. Helium is in the first energy level, so it's going to have a principal quantum number of 1. The L value is going to still be 0, which tells me that it's an s orbital. The m sub L is going to be 0 as well, and the m sub s is going to be. Alright, now here's the difference. The first electron had a positive 1/2. The second electron, it has to have a different quantum number, okay? You can never have the same set of 4 quantum numbers for 2 different electrons. So this one has to have the minus 1/2 spin. That's what allows these two to stay together in the atom. Remember, one is spinning clockwise, one is spinning counterclockwise. They generate a magnetic field which allows them to stay together. Okay, so let's look at the next example down here when n is equal to 2. So we're in the second row of the periodic table. Alright, so what are all the possible values? If n equals 2, then L can be 2 things. Alright, remember it's all the numbers, all the whole numbers from n equals 1 back down to 0. Okay, so L is going to be 0, and it's also going to be 1. Now, it's not going to be both of those at the same time. It really depends on which electron you're talking about, but these are just the possible orbitals that that electron you're talking about could belong to. Alright, well, the L equals 0 is the s orbital, the L equals 1 is the p orbital. Okay, so this is going to be a spherical shape. These are going to be like dumbbell shapes. The m sub L is going to be all the numbers from negative L to positive L. So if we take L to be 0, if the electron that we're talking about fell in the s orbital, then L would be 0. So m sub L would be all the numbers from negative 0 to positive 0, which is just going to be 0. Since we're in the second energy level, that's going to be the 2s orbital, and there's only one of them. Okay. Now, if the electron we're talking about fell into the p orbital, then we would go from negative L, which would be negative 1, then we would hit the next whole number, 0, and then we would hit positive L, positive 1 here. So that's going to be 3 orbitals here, and that's going to be 2 because we're in the second energy level, p because it's in the p orbital, and then remember the whole point of the ml quantum number is to tell you its orientation, that orbital's orientation. So 2px, 2py, 2pz. Okay, and remember that p orbital looks like dumbbells. So we would look, if we had drawn, that looks bad. If we drew a Cartesian coordinate system, we might have a p orbital on the y, we'd have a p orbital on the x, and we could have a p orbital on the z axis. Okay, so that would be our 2px, 2py, 2pz. Okay, and then we would have spin quantum numbers for the electrons that fell within these orbitals. It could be plus 1/2, meaning it's clockwise, or minus 1/2, meaning it's counterclockwise. Okay, now remember, every orbital here, that's one orbital. It's got 2 lobes to it, but it's one orbital. That can hold 2 electrons. Okay, and then the next orbital can hold 2 electrons. Okay, and then finally the last orbital can hold 2 electrons. Alright, so that means that there's a total of 6 electrons that could be in that molecule, or excuse me, in those orbitals. So maybe we've got one here, 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 and here. There's our 6 electrons flying around, okay? And if we were talking about maybe, and these are valence electrons, by the way, so maybe we've got an atom that's got all 6 of these electrons plus the electrons in the second energy level completely filled. And remember, the second energy level can hold 8. So that would be 6 electrons here plus 2 more electrons in the s orbital for a total of 8 electrons. So even further, there might be some kind of there would be a s orbital in here, and that's that spherical orbital, and they kind of all overlap that one. And there could be another 2 electrons inside of that 2s orbital. So there's our 8 electrons in the second energy level. Here's a better picture of what that second energy level would look like than my drawing. Here the yellow in the middle represents the 2s orbital, and then here you see the lobes of the 2px, 2py, and 2pz orbitals and how they are oriented in 3D space. So one is up and down, one is side to side, and then one is coming out towards you and going back away from you. And so just like before, each of these would be able to contain 2 electrons because every orbital contains 2 electrons. And so that makes up all 8 electrons of the second energy level. Now inside of this yellow 2s orbital is a smaller 1s orbital. Okay, so if I were to try and draw that in here, and it is again a sphere, right? Okay, and so inside of it there would be 2 electrons. Alright, so if we had like a hydrogen atom, there'd be 1 electron inside of here. If we had a helium atom, there'd be 2 electrons. If we moved up to the third element in the periodic table, lithium, then we would have to go beyond the 1s orbital and we would move into the 2s orbital. That'd be this yellow sphere, and there would just be 1 electron. And then we went to beryllium, and there would be another electron in here. Then we would add the 2px orbital, so that'd be this green one. So we'd have a boron, maybe boron's last or valence electron is here, and then carbon, and so on and so forth. So we could start filling those up. And then if we filled all of those up, and then we would move to the 3s orbital, and that is another spherical orbital that would be larger than all of these. Okay, and again it's spherical in shape, so I'm going to try my best to make that a sphere for you. And it's larger because it's higher in energy, so the electrons that fall within this sphere are going to be higher in energy than any of the electrons in this stuff in here. And we can hold up to 2 electrons in this 3s orbital. Okay, and then beyond the 3s we could play the game again and add another set of p orbitals. Okay, so we could have the 3py and x and z for that. It could just keep getting bigger and bigger and bigger. Okay, so last example here, n equals 3. So that means we can have an L value of 0, an L value of 1, and an L value of 2. So that corresponds to S, P, and now a D orbital. So here are all the possible ML values. So if L equals 0, ML is going to be 0, and that's the 3s orbital. If L was 1, then ML can be -1, 0, and +1, so that gives us the 2px, 2py, and 2pz orbitals. And then if L is equal to 2, then ML can be -2, -1, 0, 1, 2. So this lets us count up the number of orbitals. So we've got 1 s orbital, we've got 3 p orbitals, and we've got 5 d orbitals. Okay, and remember each of these orbitals can hold 2 electrons. So 2 here, 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 and here. And then each of those electrons can spin clockwise or counterclockwise depending on their partner. Okay, so let's see if we can answer some questions about an element's electrons using our quantum numbers. Okay, so we're going to start out easy with helium. The question is, write the complete set of quantum numbers that represent the valence electrons for the following elements. Okay, so starting off with helium, which we did a little bit earlier, we have this electron and we have this one. And so that is helium's valence electrons because helium only has one energy level, the very first one. And so that is its outer energy level, which is what valence stands for, the outer energy level. So, I want you to take a second, get out a sheet of paper or whatever, and write down what you think the quantum numbers are for this electron, and then write down what you think the quantum numbers are for that electron. Take a second to do that. Okay, so let's go through this and see. Helium's in the first energy level, so n equals 1. If n equals 1, L has to be 0. If L is 0, ML can only be 0. And the first electron that it's got is going to have a clockwise spin, so it's going to be plus 1/2. The second electron is going to have the first three quantum numbers be exactly the same, but the fourth one has to be different. Remember, no two electrons can ever have the same set of four quantum numbers, so there has to be a difference. And here's that difference. That second electron is going to have a minus 1/2 number because it's going to spin counterclockwise. Okay? Alright, see if you can do bromine next, okay? It's got 7 valence electrons, so plan that out. What energy level do the 7 valence electrons belong to, and see if you can figure out what all of the quantum numbers are for every one of those 7 valence electrons. And we'll come back in a second and see how you managed. Okay, so here I have the Bohr model for bromine, okay? And remember, the question asked about its valence electrons. So if you look at bromine on the periodic table, it's got an atomic number of 35. That means there are 35 protons and there are 35 electrons. And you have to work up adding the maximum number of electrons to each of the previous energy levels until you get to its valence or outer energy level, and then you add your last number of electrons, okay? So remember, in the first energy level we have 2, then the second one we have 8, then the third one we can have 18, and finally in the fourth energy level we could have 32 electrons. We don't, but we could, okay? As it turns out, we end up with 7 electrons left over, so bromine's got 7 valence, and we need to identify the quantum numbers for each of these 7 valence electrons. Okay, so I'm going to walk you through that over here on how I came up with each of these things. Okay, so obviously all 7 of these electrons, these valence electrons, are in the 4th energy level, so all of the n values are going to be 4. Okay. All right. Okay. Now the next numbers here, L. Well, if we do our thing for L and say that it is n minus 1, okay, then that would be 4 minus 1, which equals 3. So one of the possibilities is 3. Okay, and then we could have 2, 1 for L, and also 0. Okay, and remember that each of those corresponds to orbitals, s, p, d, and f. Okay. Well, one thing that we need to remember is that orbitals have different energies. Okay, and so, I mean, we could excite those electrons. Remember, we talked about ground state and excited state. Okay, and we could bombard those valence electrons with photons of light, which would cause them to jump up into higher energy orbitals, like the f orbital, okay? But electrons like to be in ground state, Okay, and so we are always going to assume, unless told otherwise, that the electrons are in their ground state. So we need to start with the lowest energy levels first. Okay, so here we said we're in the fourth energy level, so that's right here, and that energy level is going to split, and we're going to have a 4s, 4p, 4d, and 4f, and this is all according to its energy. So 4s is lower energy than p, and so on and so forth. So you'll notice here that my L value that I'm choosing is 0 because that corresponds to the s orbital, which is the lowest energy of the fourth energy level. That's the lowest orbital there, so that's the one I'm starting with. Okay, so I've got L equals 0, and that's going to give me that s orbital. So this is our 4s. If L equals 0, then ML has to be 0 as well. That gives me the orientation. And of course there's only one way to look at a sphere. And it's going to have a plus 1/2 or clockwise spin. Okay, so maybe that is this electron right here. Okay, and I've got my clockwise spin there because I pointed the arrow up. Alright, so then the next electron is going to have the exact same beginning 3 quantum numbers, and then we have to make our change right here because no 2 electrons may have the same set of quantum numbers, so we have this counterclockwise spin, so maybe that's that electron. Okay, that means that the 4s orbital is filled because an orbital can only hold 2 electrons, so then we have to move up to our p orbitals. Okay, so in that case our L value is now 1. 1 corresponds to a p orbital. Okay, and so then the ML values are going to be all the numbers from negative L to positive L, so that's going to be -1, 0, and +1. Okay, so then we get a plus 1/2 electron here, and we're going to get a plus 1/2 electron here and a plus 1/2 electron here. And you might be saying, well, wait a second, why is there no minus? We saw in an earlier video Hund's rule. I didn't actually go into any detail on that yet, so let me address that situation now. Hund's rule says that every orbital has to get 1 electron before any orbital gets to have a second electron. It's kind of like a buffet line, okay? Everybody gets to go through first before anybody gets to come back through for seconds, okay? It's only fair. So we can say that this electron, and this electron all belong to the p orbitals, px, py, pz, and they're all going to be clockwise spinning electrons because they are the only electron in that orbital so far. Okay, and then we get to the last set of numbers. Okay, we're still the 4th quantum number. L is still equal to 1 because the p orbitals are not all the way full yet. Okay, each one of them only has 1 electron so far. So we're going to go back to the px orbital and give it its second electron, which means that that electron has to be a counterclockwise spin. So our last electron here still going to be in the 4th energy level. L is going to be 1, which means it's in a p orbital. ML is 0 this time, so that means that it's going to be in the 4p y orbital along with this electron, and therefore it needs to have a -1/2 or a counterclockwise spin. Okay, and that covers all of our electrons, or our valence electrons for bromine. So hopefully you'll be able to answer similar questions in the future. Here are 2 other things we need to know because we might be asked types of questions that would require us to do this. We've already worked with this type of question before. I'm sorry, it's this kind of question. For the total number of electrons that can be held within an energy level. That one was 2n squared. Okay, so we've already been doing this actually. Here the example is, what if n equals 4? Okay, 4 squared is 16. 16 times 2 is 32 electrons. And where do those 32 electrons go? Okay, here's the breakdown of that. The first 2 electrons go in the s orbital. Then 6 of them go to the p orbital. Then 10 of them go to the d, and then 14 of them go to the f orbital. Okay, so if you take 2, 6, 10, 14 and add them all together, you get 32. So the 2n squared, it works. It tells you how many maximum number of electrons can be held in any given energy level. Okay, now what if you wanted to know the number of orbitals found within any given energy level? That one is just n squared. Okay, so instead of multiplying it by 2, which it stands for the 2 electrons that every orbital can hold, here we just have n squared. That tells us how many orbitals there are. So what if we said n equals 3? 3 squared is 9, so there should be 9 total orbitals in the third energy level. Let's see if that plays out. You would have one s orbital, okay? You would have 3 p orbitals, that would be the px, the py, the pz, and then you would have 5 d orbitals. Remember right here, when n equals 3, here's our d orbitals. We would have 1, 2, 3, 4, 5 d orbitals. Okay, remember when L equals 2, we're talking about a d orbital. So if you take 1, 3, 5 and add them all up, we get 9. So the number of orbitals that an energy level can hold is the same as n squared. So that one works also. Alright, so you should be able to answer any question about quantum numbers that I can throw at you. You should be able to draw pictures of the orbitals, fill them with their electrons, calculate the maximum number of electrons possible in an energy level, the total number of orbitals there are, and you should be able to relate these to the Bohr model of the atom. Now please understand that that model of the atom is outdated. Because of these quantum numbers Schrodinger's equations gives us, we now have the cloud model of the atom, which would look something like this. So this one's showing us a 4s orbital encompassing a 3D xz orbital. So the red dots are the 4s, and notice that on the whole they look to be in this spherical shape or a circular kind of shape for us. The 3dx one here, that one's a little bit more difficult for us to kind of make out. Hopefully you can see that we've got these lobes here. Alright. And here is what a dxz orbital looks like. Okay, we've got our 4 little lobes here, and they're supposed to be in this plane right here along the x-axis. Now they've kind of renamed their axes here, and I suppose that that's standard for orbital notation, or as far as the shapes go, so we can kind of look for that, but it may be a different plane that they're showing us in the cloud diagram that we're going to look at here in a second. Overlapped with all of them, that would be a completely filled up d orbital if we overlapped all of these images together here. Let's go back and look at our cloud model. Okay, when I'm looking at it, I'm really seeing my lobes in this plane that is directly facing me. So if I were going to say it was anything, I'd say it was a dyz orbital. But remember, this molecule or this atom, excuse me, that we're looking at could be rotated in 3D space. It could be flipped around in any kind of direction, and so depending on which way I look at it, might make me think I'm looking at a different orbital. So to me it looks like a YZ, but apparently the way that this image was taken was from the XZ view. Okay, so anyways, this is on the picometer scale. So that shows you how very small this is. If this is 300, then that's 200, there's 100. So like all of the 3D orbital here is within 100 picometers from the nucleus, so that's pretty cool information to know. So please understand that this cloud model of the atom here, that's the new and accepted model of the atom. The Bohr model of the atom is really outdated. We know that that's not true anymore. We have these probability clouds, and that's what they're called. That means that we have the likelihood or the probability of finding an electron within this region of space. Okay, we're not guaranteed that it's going to be there, but I think there's like a 90 to 95% assurance that it should be there. Okay, all of these quantum numbers that we've gone through and the orbitals that the electrons fall into and what spin they have, all of that can be notated in several different ways called electron configuration, and that is what we're going to get into in the next video. Thank you so much for learning with me, and I will see you next time.